Hello. In this talk, I'm going to present a paper towards a unified agent with foundation models, accepted as an oral at the Reincarnating Reinforcement Learning Workshop at ICLR 2023. Large language models and visual language models like Chinchilla and Flamingo have demonstrated outstanding capabilities. They are able to quickly infer human intentions from few examples, reason logically, plan, and possess remarkable common knowledge and common sense. So this work is motivated by the following question. Can we use the capabilities of these models to create more general and data-efficient reinforcement learning agents? Generally, a reinforcement learning agent implicitly maps observations to actions using one or more neural networks. But in this work, we put language at the core of the agent, using foundation models as the main reasoning tool. In order to do that, we need a few building blocks. First of all, we need a visual language model, a VLM, to map image observations into language descriptions. We then use large language models, LLMs, to take this text together with the current task of the agent and output a description of what the agent should do, still in the formal language. And finally, we ground this language into actions using a language condition policy. We use a pre-trained clip as the VLM and fine-tune it with data that we generate in simulation, as we will see shortly. The language model is taken off the shelf. We use an instruction fine-tuned large language model, FLAN-T5, and all the policies are trained from scratch, as we will see. We test our framework on the RGB stacking robotics environment, an open-source Mujoko environment from DeepMind. Here, a robot arm interacts with three color objects, and its goal is to stack them into a goal configuration selected by the user. We use the Mujoko state of the robot and the objects as input to our policies, the X and Y coordinate where to pick or place as the actual space, and use image observations from cameras mounted on the box as inputs to the VLM. This is how CLIP, the VLM we chose, works in a nutshell. Its goal is to map visual observations into matching textual descriptions or captions. CLIP has an image branch that takes visual observations and maps each of them into an embedding vector. It also has a text branch that maps sentences into embedding vectors of the same dimension. To compute how well the textual description fits an image, we compute the dot product between the embedding vectors given by the image and the text branches. The larger the result, the better the match. The problem is that CLIP, trained on internet scraped images, does not work that well out of the box for our task that involves precise manipulation of objects. As you can see for this observation, both correct and wrong descriptions, respectively in green and red in this bar plot, obtained similar scores. And therefore, we decided to fine-tune CLIP on data that we gather from our domain. After fine-tuning, the scores vary much more in magnitude, and it becomes much easier to define a threshold that separates correct and wrong descriptions. So how much data do we need to fine-tune CLIP? We conducted an investigation to understand the performance increase of CLIP as a function of the size of the fine-tuning dataset, and we noted that a dataset of around 1,000 image text pairs is enough to obtain satisfactory results in terms of precision and recall. We obtain a large precision, which is fundamental to avoid noisy or wrong textual descriptions. Now we'll see how this framework allowed us to obtain remarkable results in a reinforcement learning setting, exploring and learning new tasks from scratch. Let's talk about one of the main challenges in reinforcement learning, exploration. We will see how language can dramatically improve an agent's ability to explore and collect data. So as quickly described before, we use the stacking tasks in the RGB stacking environment. The goal in this case is to stack the red object on top of the blue one. These tasks have a sparse reward. Only when the stack is complete, the agent receives a reward from the environment. And this happens rarely when randomly exploring, making the task challenging to learn. So here's how we use language to speed up the process. As the task is formulated in natural language, we ask a language model to decompose such tasks into a series of sub-goals. In this case, stacking the red object on top of the blue is decomposed into first grasping the red object and then putting it on top of the blue. Having this language curriculum, this language plan, we can now use the VLM to see if any of these sub-goals happen at any step in the trajectory. In this case, we see that the VLM detects that the robot has grasped the red object during the episode. Therefore, it labels that transition with a reward. And in our experiments, these self-generated rewards for picking up the red object happen 20 times more often than the sparse stacking reward, making the task much faster to learn. And indeed, here's a comparison of the agent using the language curriculum and its additional rewards, and the same agent using only the environment rewards. Here we plot test time successes at stack in the red and blue. Our agent is substantially faster at learning, and we can see that when our agent has reached around 50% success rate, the baseline is still below 5%. Here's a quick overview of our exploration framework inspired by the collect and infer paradigm. Many agents collect data following the plan proposed by the language model. Their experience is collected into a buffer, and the VLM then hindsight relabels each trajectory with possible rewards, detecting if any of the goals proposed by the language models are achieved. We use these labeled trajectories to train a policy that is then used to guide the agents, and the cycle goes on and on. We then tested our method on an even more challenging task, the triple stack. Triple stack is orders of magnitude sparser. A reward is received as an estimate every million steps when randomly exploring. Normally, the environment will give a reward only if the three objects are correctly stacked in a stable configuration. To accelerate learning, we use the same approach. We ask the language model to decompose the task into sub-goals. In this case, the number of sub-goals is larger as there are more steps involved into solving these tasks, and the language model understands that by itself. The VLM detects if these sub-goals are reached at any time during exploration, providing additional rewards. And in this case, this process is even more important, as these additional rewards are obtained orders of magnitude more often. In this task, the difference between our agent and the baseline is even more clear. While our method is effectively learning to solve the challenging task, the baseline agent still has to receive a single reward from the environment. Comparing three tasks with varying degrees of sparseness, we can observe an interesting trend. We define the sparseness of a task as the number of steps that a random policy will need to receive a reward on average. With our framework, the number of steps needed to obtain a certain success rate grows more slowly than the sparseness of a task. This is a critical result that suggests that sparser tasks can become tractable using our interplay of language models and VLMs. Now we will talk about another fundamental challenge in reinforcement learning, the ability to extract skills from offline data and to transfer knowledge across tasks, therefore learning sequential tasks more efficiently. Anytime our agent collects data to learn how to solve any task, we add each trajectory to an offline lifelong buffer. Let's say we want our agent to learn a new task. So we create a new empty buffer that we want to fill with successful trajectories for this new task. We use the language model to decompose a new task into a series of sub-goals as before. But now, before we start exploring, we use the VLM and this list of sub-goals to extract successful trajectories for this new task from our offline buffer. We extract all trajectories from the offline buffer and use the VLM to see if any of these trajectories has successfully completed any of the sub-goals. We then collect all the trajectories that have successfully completed any of the sub-goals into this new buffer. Now, the agent does not need to learn the new task from scratch. We can run any offline reinforcement learning algorithm on the relabeled data collected in the new buffer and obtain a policy that can be used right from the start to perform better guided exploration. In this bar plot, we show how sequential task learning becomes more and more efficient using our framework. We show how many interaction steps are needed to obtain 50% success rate on three tasks learned in succession. First stacking the red object on the blue, then the blue on the green, and finally the green on the red. The agent, when starting its learning process of a new task, relabels all the data collected up to that point in previous tasks for the new task. As you can see, the agent needs fewer and fewer interaction steps to reach that performance on new tasks, as you can effectively reuse past interaction data, although it was gathered for a different task, through hindsight relabeling. The third aspect we focus on is scheduling learned skills to solve novel tasks. Once the agent has learned a series of skills, we can use this framework to combine them to solve novel tasks. So the agent receives a language description of a new task at test time, and we use the language model to decompose it into sub-goals and obtain therefore a plan to tackle the task. We use the current state and the sub-goal to reach as inputs to language condition policy. We execute the action predicted by the policy and transition to a new state. We then use the VLM to predict whether the desired sub-goal has been reached. We continue using the current sub-goal as input until the VLM predicts that it was reached, based on the current observation. Once that happens, we select the next subgoal from the list generated by the language model and continue. So with this framework, the agent can keep retrying a certain skill, a certain subgoal until it was reached according to the VLM, and then it can go on to the next step of the plan. Finally, we describe how this framework allows the agent to imitate other agents through observation. So in this case, we have a human operator demonstrating a task to solve. The agent only receives the series of visual observations. Given the list of sub-goals it has learned to tackle during training, it can now use the VLM to capture the video frame by frame. The VLM predicts what sub-goal, if any, was reached in each frame of the video. We therefore obtain a list of sub-goals that the agent needs to emulate. We give this list of sub-goals to the agent and execute them as described before. The result is the ability to one-shot learn from observation, even from human videos. In conclusion, we presented a method that can effectively tackle a series of core reinforcement learning challenges that normally require vertically designed algorithms through a general, more unified, language-centering approach. We believe this research avenue can lead to the development of more generally capable agents. Thank you for your attention. I want to thank my co-authors that made this work possible, and we invite you to read our paper for more details on our work. Thank you very much.